Hey guys, how you doing? It's Coach Scott, and here we go again. Now I got a new unit where we're talking about the atomic structure, right? Well, let's start talking first on this subject with the Bohr model. Some of y'all might recall this from previous classes. Okay, so the Bohr model, okay, it was a pretty good little model that we come up with. All right, and now let's look at our history of where we're at. Okay. We talked about this in the last unit. So Democritus, in 460 BC, he did different than Aristotle, and he had a different school of philosophy. And in his opinion, that everything was made of very small things you couldn't see. He called them atomos, right? Then in 1803, everything stayed pretty much stable. Then in 1803, and then Dalton had six postulates, which more or less suggested that Democritus was right. It's not just earth, fire, wind, and air, right? And then in 1897, about 95 years later, J.J. Thomson discovered the mass-charge ratio of the electron, hypothesized about the electron, discovered the electron, and he came up with the plum pudding model of what the atom was like. Then a student, Ernest Rutherford, did the gold foil experiment, and he came up with our modern nuclear model of the atom, as far as where the nucleus is and electrons. And his theory, of course, said that most of the atom is empty space, had a very dense, very small nucleus in the center of the atom, and it was surrounded by mostly empty space and electrons. So, we know that atoms are composed of protons, neutrons, and electrons. The protons and the neutrons make up almost all the atom's mass and are found in that very small nucleus. And then the electrons are outside the nucleus, and they will occupy almost all of the atom's volume. Okay, that's what we know. We learned from Unit 1. Again, just a little quick review. All right, that we know that the protons and the neutrons are so much heavier, almost 2,000 times heavier than an electron. All right, and the protons and neutrons, you can think of them as being stationary right there in the center of the atom in what we call the nucleus. So these electrons, they'll move around so rapidly that we can never know that location, right? We're never certain about it. Now we call that, excuse me, an electron cloud. So this electron cloud is around the nucleus. We know that a proton has got a positive one charge, and the electron has a negative one charge. And the neutron, of course, does not have any charge. So, as far as the volume, so we know that the volume of the parts of the atom are near zero compared to the volume of the atom, right? So if we say that the nucleus has a diameter of 1 and the volume of 1, the electron has almost no part of the diameter, and it has like no part of the volume. All right, so now we look at the diameter of the atom. The outer parts of the atom is 10,000 times bigger than the diameter of the nucleus. And the volume of the atom is 1 trillion times the nucleus. So there's a lot of volume to that atom compared to the nucleus. Wow. So this is what we can say. We'll take a break, get the answer on this one. A proton has what type of charge, while an electron has what type of charge? Give you a second to answer it. We'll do a little double check, pause. And of course that answer is that the proton has a positive charge while an electron has a negative charge. That would be C. All right, another one. The mass of a proton is about blank more than that of an electron. Pause, come back with your answer. D, 2,000 times more. The mass is 2,000 times the protons than that of the electron. Try another one. The diameter of an atom is about blank larger than the diameter of its nucleus. Pause. And if you answered D, 10,000, you would be correct. So, Rutherford, when he figured this out, he was shocked. So if you go to the Liberty Bowl, right? Y'all been to Liberty Bowl, it's pretty big. And we said that's the size of an atom, the size of the Liberty Bowl. Right, pretty big. It was a sphere. If you were to say the nucleus, right? This is a nucleus, and you were to make it the size of a pea, you would put that in the center of the stadium, in the center of the Liberty Bowl Stadium. So the electrons would be too small to see, you couldn't see them, and would be constantly moving all around the stadium. So, even to the edges of the stadium. So the amazing fact about these atoms, they're empty. There's mostly empty space, and we just learned that about 100 years ago. Think about it. The atoms that make up me and you, the atoms that make up the desk in front of you, your TV right now, your computer, they're mostly nothing. Now always remember this, there's not air in those atoms, because air is atoms, so they can't be atoms. It's nothing. So, this is true of all atoms. Atoms are almost completely empty space. So, why can I pick this pin up and flick it? If most of these atoms that make up this pin and the atoms that make up my finger, they're space, why do I feel it? Why does the world feel solid? Think about that. Let's answer. So, the repulsion of the electron clouds within the atoms, right? And negative charges, we know, repel each other. That's what makes stuff feel solid. When you kick a ball, the electrons in the ball interact with the electrons in your shoe, and that's what provides the kick. When my fist goes up against your face, we don't want to use that example. When I take my hand and I clap, and that's what I hear because it's making sound waves. But why doesn't my hand go in between each other? It's because these electrostatic repulsions of the electron in the atom. They're called Coulombic repulsions, and we'll go over those over the next several months a lot. And so, these electrons are responsible for the chemistry of these atoms. So, we notice some problems with the nuclear atomic model. Since atoms are almost completely empty, there's nothing in there. There's nothing to keep the electrons and the nucleus apart. So, a positive charge and a negative charge do what? They attract. So why doesn't that negative electron smash into that positive nucleus? By this model, that's what should happen. So why don't they collapse? Think about an answer. Put it in your notes. I'll pause. Here's why. Positive and negative charges attract. Why don't the electrons fall into the nucleus? Okay. Maybe they orbit around the nucleus like the planets orbit around the sun. But if this was true, they would constantly be accelerating as they orbit around the nucleus. Now, when an object accelerates, a charge accelerates, it'll radiate energy in the form of light. So that would mean we would be glowing, right? We would be emitting light. We'd be like aliens. Does that happen? Oh, and if you emit light, that means that electron would lose energy. So all the kinetic energy in that electron would be radiated away in about 1/1000th of a second. And guess what? The electron would fall into the nucleus and the universe would collapse. Has the universe collapsed yet? No, I'm talking to you. So we know that atoms are stable, they don't collapse. So if an atom's electrons were continuously orbiting the nucleus, they're going to radiate energy and collapse in 1/1000th of a second. So we don't see that. So we're going to answer this question on why not. Right? So atoms do not emit light most of the time. We don't glow. We have a need for night lights if we want to get up and go to the bathroom, right? So if an atom's electrons were continuously orbiting the nucleus, they would radiate light, but they don't. Why not? And atoms do emit energy. It only consists of specific colors, and we'll do an investigation into this in the next couple of weeks. Most of these colors are absent, and all we see are narrow bands of light, narrow lines of color. So this is a hydrogen atom that's been excited. So we only see the yellow bands right there, the black bands. That's all we see. Why? That's what we're going to answer in this unit. So let's check a little bit. Physics predicts that accelerating charges emit light energy. Always, sometimes, never, none of the above. Pause, answer, see what you think. Come back, here we go. Always. Accelerating charges emit light energy. We'll do another check. When atoms emit light, what is observed? I'll pause. And what we see when an atom emits light is an emission spectrum of specific colors only. Okay, do another one. Why was the nuclear model insufficient? It could not explain why only specific colors of light are emitted by atoms. It could not account for the stability of the atom. It required the electrons to be in the nucleus, the protons that orbit around the nucleus. Are A and B, or I need some help. Pause. And we're back. If you said A and B, you would be correct. So guys, that's the end of our introduction. We're going to have some exciting discussions about atomic structure. You're going to learn some things you did not learn in 8th grade or 9th grade science. Okay? And we're going to challenge your mind and your understanding of the world as you know it now by taking some of the things you know, adding it to some more, discovering some more neat stuff, and get a better understanding of what's going on in the world. So anyway, this is Coach Scott saying, have a good night. And keep red deviling. Bye.